Welcome, everyone. I am Professor Stephen Dow. I am not Professor Guo, who is out today with an injury. He will be with you the rest of the quarter. If you're here for this class and taking credit for the class, please sign up in the back there. And I'm very happy today to introduce our speaker, Haoqi Zhang from Northwestern University. He's in the Department of Computer Science there. Prior to that, he was a postdoc at MIT, and he did his PhD at Harvard in computer science and economics. Is that right? Sort of?
That's good.
And what can I say about Haoqi? Haoqi and I go back quite a ways. He has a very good relationship with Stella, his dog. And Stella is everywhere you see Haoqi, you see Stella. They've been surfing together. They've been on a paddleboard together.
Yep.
I found out this morning Stella came with them here to San Diego. So that's just something about Haoqi. You can get to know him. He's a great guy. And today he's talking about computational ecosystems, which sounds really fascinating. And let's hear more.
Awesome. So thank you, Stephen, and hi, everyone. So in this talk, I want to share with you how I worked really hard over the last couple of years to align my work with my values and my hopes for the world. Okay, and I'll say more about that, but my hope for this talk is not that you walk out of here with my values, but instead that you're inspired to think a bit more about your own and to realize them. And I think that'd be really wonderful. To be able to do that. So with that, I'd like to share some thoughts on computational ecosystems and what they can do to advance human values at scale. Okay. So as I've come to learn more about my work over time, I've come to realize that the general challenge underlying all these problems that I cared about is how can we create scalable solutions to human problems and advance desired human values in the absence of a technology that can overcome real-world constraints. Okay, so as somebody who's in computer science and who designs technologies, this is a pretty unfortunate question to be asking, right? Because how do you do it? So let me just give you an example of one of these problems that I came upon. So not long after I started at Northwestern, I began mentoring undergraduate students in research through a new program that I started called Design, Technology, and Research. So when we started in spring 2014, I just had 7 students. But not long after that, in about 2 years, I was mentoring over 20 students on 14 independent research projects. And very quickly, I learned this scary truth that faculty time doesn't scale. Like faculty time, it's like anyone else's time. It's like a fixed block. You can't stretch it and make more time. Okay? So as an example of that general challenge I talked about earlier, the question is, how can a single faculty mentor train 20 plus students, right? So scale solutions to this, for cultivating self-directed learners who are autonomous and who are capable of tackling complex problems out in the world so that they could actually build new knowledge. Right? This is the value that I cared about in this setting, but in the absence of a technology that scales my time, right? So this is the real world constraint part that unless we have a way to deal with this, we're not gonna scale this. Okay. So this question is really hard because the best human solution we know, which is excellent, but unfortunately it doesn't scale very well. Okay? And this solution is apprenticeship. So it's also called one-on-one mentoring, right? So you work with someone very closely, and it's a highly effective model of training people to do very complex tasks, such as research. But as Alan Collins reminds us, and Alan Collins is kind of the godfather of cognitive apprenticeship, so thinking about how to do apprenticeship, but for stuff of the mind, he says that apprenticeship requires a very small teacher-to-learner ratio that's not realistic in the large educational systems of modern economies. Okay, so somewhat depressing fact. And unlike for some other problems where there's a best machine solution out there, here it's not clear that we actually have a good machine solution in sight. So software can certainly provide helpful prompts to guide student thinking. We do some good design work there too, but no AI technology is really ready to replace the mentor in the foreseeable future. And one of the main challenges, of course, is that we lack a model of both the problem domain, which is solving complex ill-structured problems, but also a model for instruction, right? The kind of things that we would want to do in research and design generally fits into this category.
Actually, how would you fit, I guess I feel like the two things that come closest today
Yeah.
are in some very domain-specific ways. You have cognitive tutors, and we do have a model.
Yep.
The other one is YouTube.
Yep. Where we kind of have a model too, right?
Well, I guess I mean that.
Yep.
That's exactly right. So with cognitive tutors, you have a computational model of the learner.
Yep.
And with YouTube videos, hopefully the person on the far side of the camera has a model.
Exactly. Right. So I think that's exactly the kind of problem we're facing, is that when our technologies, whether it's the YouTube or the cognitive tutor, can't quite get a model for the thing that we want to do. And I'll give you a very specific example of that way later in my talk. What are the options we're left with at that point? And I think research is one of those examples where it's like, maybe one day we'll have a super rich model, and maybe it'll be wide enough that it's not just for a very concrete problem. But that's where we are right now.
I guess I feel like this quote just needs a for most domains.
Oh, absolutely. Sorry. So yeah, this is.
In some cases, the answer is yes.
Yes. Sorry. This quote is directly addressing the challenge of teaching students to be self-directed learners for doing independent research, let's say in HCI. But yes, this quote is connected to the previous slide. That's a great question. Thanks. So as I was talking about options, we have very few options available for this specific problem, right? So we could wait for a technological silver bullet, which could take quite some time, or it may never come. We could also compromise in a variety of ways, right? We could say, forget undergraduate research, let's really figure out how to get lecture right and scale that, which is, good, you could do that. You could also just say, I'll just train a small set of elite students, right? So I give up on the scaling part, but I'm still training students. And I think the one thing that I want to note, though, is in each of those cases, you are giving up something, right? So you're solving some other problem, which could be very important, but you're not realizing this set of values for this problem, at least in this case that I cared about. And a lot of the questions I've been asking, right, faced with this is, what is this or? Is there an or that we could tap into for approaching these kinds of problems? And over the last 5 years, this general question has led us to the design of what I call computational ecosystems. And what computational ecosystems are is an interleaving of community processes, social structures, and intelligent systems that invite and unite people and machines to overcome these larger challenges together. So what you're seeing from this diagram is that computational ecosystems incorporate many components, right? And without getting into any individual component in detail, the thing to think about is how to design all these components as a whole, as a collective system. Okay? And our focus on the systems approach to thinking about design echoes the calls from people like Atul Gawande from the Harvard Medical School, who argues that in essence, having great components isn't actually enough. So Atul says, we've been obsessed in medicine with components. We want the best drugs, the best technologies, the best specialists, but we don't think too much about how it all comes together. It's a terrible design strategy, actually. And Atul goes on to say that making systems work is the great task of our generation of physicians and scientists. I would go further to say that making systems work, whether in healthcare, education, climate change, and making a pathway out of poverty, is the great task of our generation as a whole. And this call for system-level thinking is happening in fields like artificial intelligence as well. So here I have a quote from Eric Horvitz, who's the director of Microsoft Research, and he says, I'm pretty sure that the next leaps in AI will come from integrative systems rather than wedges. So wedges being components or wedges of intelligence. We need to focus on building a system where the whole is greater than the parts. And closer to home, in HCI, there's been similar calls for a need for system-level thinking. So one of these calls comes from George Furness, who in this wonderful paper called Future Design Mindful of the Morass, talks about it's likely that our designs will be more successful if we become more mindful of this larger picture, this mosaic of responsive adaptive systems. And what George is referring to is that if we're designing applications, if we're not aware of all the other stuff that's happening around that application, we're not quite going to get it right, and we're not going to have as much success than if we were aware of that full picture. And I think it's wise for us to heed George's words here, but as it turns out, we're going to do more than just to be mindful of this larger system when designing applications, okay? And what I'm going to talk about today is we're going to design the entire system. So to design the entire system, I'm going to take a socio-technical approach to design, as you may already be familiar with, but I'm going to extend it to account for some of the added complexity of designing the whole system as a whole. Okay? So let me just walk you through some of these ideas. So for instance, when designing a socio-technical system, typically we do consider the context of the larger system, but in practice, the solutions are often created component by component or layer by layer. Okay, so for example, we may think about supporting group collaboration and focus on new collaborative technologies for doing this, right? And then we might go work on a problem and create technologies for coordinating crowds. But what we're really interested in with computational ecosystems is understanding how to bring multiple structures at these different scales together and think about how the interactions across them can jointly solve a problem. Okay? And this is going to allow us to explore some potential synergies that happens when these components interact with each other to create new solutions. So let me give you another example. So another way you could think about designing socio-technical systems is you go layer by layer, right? So you come up with a good community process, and then you design the social structures of your organization and the interactions to work with that process of working. And then you go ahead and think about, right, understanding exactly what's already going on in the organization. So you're being very mindful of the setting that you're creating in, creating these intelligent systems and user interfaces to work with that. And there's nothing wrong with this. This is actually a very mindful approach in thinking about design. But what I like to be able to do is to explore opportunities to think about some of these vertical slices all as one, right? So if we didn't fix on the process or on the social structures first and then do the tech, are there new opportunities to design entirely different combinations of processes, social structures, and technology that work together? So in summary, the idea then is that computational ecosystems is giving us an opportunity to design simultaneously all the components of a socio-technical system as a single integrative solution. Right? So we're still going to be thinking about people and technology, but we're just taking a more comprehensive approach and constructing how all these parts interact, both technically and people-wise. Okay. So to reason about the added complexity of thinking about the whole thing, we're going to adopt two helpful perspectives when designing computational ecosystems. And one of these ideas I'm going to call computational thinking, and it's the decomposing and distributing of problem solving to diverse people or machines across the ecosystem. Right? So this is just computational thinking as you know it, but really thinking about how to apply that across an entire system. And the second idea that we're going to apply is something I call ecological thinking. And the idea is to create these sustainable processes and interactions that support simultaneously the ecosystem members and what it is that they care about, and also the functioning of the ecosystem as a whole. Okay? So as I go through my talk, we'll see examples of both of these ideas coming up over and over again. So for the rest of the talk, I'm going to present to you two examples of computational ecosystems we've designed for community-based planning and also for research training. I'll then preview what's next in computational ecosystems, and finally end with some thoughts on the role of computing technologies in advancing human values. Okay. So any questions up till this part before I get into my first example?
We're with you.
Okay. I think I learned this actually from, well, I learned this from somewhere else, but I remember, I think it was in your keynote or Jim's keynote that you said, it's good to wait, so I'm practicing. Okay, good, awesome. Any questions? Yes, it worked.
When you say community-based planning, like, to how large of a community do you imagine like it actually working to?
Good, so I'll give you an example where we involve over 1,000 people.
Okay. Well,
So I have one question, which is that I largely agree with, I mean, obviously everybody in the design lab, I think, would
Right.
share Atul Gawande's sentiment that the systems piece is often under-investigated and under-attended to, and medicine is a great domain for that.
Sure.
There's a thing that he didn't say, which you could take as a misentailment, which is that doing the bottom-up stuff is handy too. You know,
Yes.
In the medical domain, for example, the value of asking about all of the connection pieces
Yep.
doesn't mean that you put no effort into the components.
Yes, I 100% agree with that. And in some of these cases, I might actually show you new components, right? So thank you for that clarification, because please don't walk away from this talk and says, oh, we don't need to design any components. We just put it all together. It's like, what are you putting together? So Scott's points, I 100% agree with. Yes, so thank you for, yes. Yeah, the hard part is you have to do both. Right. Okay, are we good? Oh, go ahead, yeah.
I'm just curious of your thoughts on this. My experience with this is that when I've talked to people who tend to be more at a systems level. And actually this built on our conversation when we were walking.
Yep.
They work in levels of abstraction.
Yep.
And then they often lack the details that they need to know. It's like a leaky abstraction problem,
Yep.
right? Where they don't realize that there's something in the lower layer that's broken.
Yep.
How do you think about that, and are you going to get into that in your example?
My examples are going to have a lot of components and a lot of components working together.
I have a hunch that would be the case.
Okay, so yeah, let's maybe walk into some of these examples, and then please feel free to repeat the question if it comes up. Okay, so let's talk about community-based planning. Some of you might have already seen some of these work, but I think you'll see a different perspective on it, even if you've seen some of this work before. So I'm going to talk about community-based planning, where we're going to focus on trying to design an inclusive process that scales and that advances the goals of its members when we're doing a planning problem. Okay, and the case study, the specific case we looked at, is planning large academic conferences. Okay, so what I'm showing you right here is a handful of ACs or associate chairs working to come up with a preliminary schedule for CHI. This is in 2012, and they were trying to construct hundreds of sessions, as you can see, on a wall, on paper, over a 2-day period. Okay, and there's about a handful of people in the room. I think no more than a dozen for sure, but right, small group of people. And immediately you can see that the organizers are facing two challenges. Right? So the first one is that they lack information about the preferences, constraints, and knowledge that's held by the community members. Now, the ACs know a lot about the conference, but CHI's gotten really big. There's over 400 papers, and they're putting together 200 sessions. Right? So there's a lot of distributed knowledge about information and just what goes together and what are the themes that are emerging, that it's going to be highly dependent on the people in the room, and the best they could do is still going to miss a lot of what people want. And then the second point is that the organizers lack tools for managing the complexity of planning, right? So they not only lack these tools on the wall, which, it's just the wall with these paper affordances, but when they go home, what they actually do is they take this initial schedule that they get, they put it in a computer, and then they go through this painful, time-consuming process where they're trying to resolve conflicts. Okay? And that's where the pain really starts, because they'll start trying to move a paper somewhere else or move a session somewhere else, and they think they fixed the problem, and then they'll create another one. Right? So you fix a problem, and then it's like playing whack-a-mole, right? You fix a problem, and it's like, but because you moved that other thing over here, you just created another conflict, right? And then the the chairs at CHI that year and the year before certainly, and the year after as well, they're just super dedicated, so they will want to spend a lot of time doing this, but it's kind of a losing proposition without good tools for resolving conflicts. So to overcome these challenges, we created a system called Cobi, which I'm going to think of as a computational ecosystem for community-informed planning. And Cobi is built on two simple ideas: engage the entire community in the planning process, and then give organizers better tools for managing the complexity of the schedule and for resolving conflicts. Okay? But of course, simple ideas, at implementation, we have to work out the components and how do we actually do this. So let's talk about engaging the entire community in planning. And to do this, we created new processes and tools for involving committee members, authors, and attendees. So we engage the committee members by to make initial sessions right after the PC meeting. We ask authors to tell us which papers they think fit in a session with their own and what talks they want to see, so we make sure that the talks they want to see is not at their talk slot. And then we help attendees navigate the schedule by recommending papers and sessions using Comfort. And we use their favorites to identify the popular sessions in the talk so that we could put those in bigger rooms. And also to see what are the talks of mutual interest that might be occurring in concurrent sessions. Right? So we like to avoid those when there's a lot of people interested in both sessions. So this is all very reasonable. And we take a design-based approach to thinking about how to design these systems. But right off the bat, there's actually some computational challenges. Okay, so let's just talk about committee sourcing for a second and making sessions. The problem is global constraints. Okay, so let me give you an example of this. So you have a paper, and this paper could fit in many possible sessions. Right, this happens all the time. But at the end of the day, it's only going to end up in one. Right, at least the current way we do conferences. So collecting a bunch of potential sessions is good, but it's not actually enough, right? Because once the paper is selected for one session, all the other potential sessions with that paper fall apart, and all those papers now no longer have a session, and so on and so forth, right? So the interdependence gives you these global constraints that make it so that you really have to think about these sessions, and you could give suggestions, but at the end of the day, they need to be kind of separated out sessions, right? A paper is only going to end up in one. So to do this, we used a tool that we created called Frenzy. And the core idea behind this is that we have a two-phase collaborative planning process that uses crowds and groups. Okay? So in phase 1, we're trying to elicit metadata from all the ACs. So we do this right after the PC meeting, and we get these possible groupings for sessions. Okay? And we use these things that we call actionable feedback. So this is the machine looking at the process at which we're solving the problem, and it's identifying the papers and groupings that need additional work and surfacing them as suggestions on that left-hand column. So the system allows for real-time collaboration across all these ACs, and they're doing this kind of goal-directed process of tagging and categorizing. Okay? So then in phase 2, you have a smaller group of ACs, right? So again, about a dozen people who work to satisfy the tighter constraints, right? So they have these flexible options that the people generated in phase 1, but they deliberate and they actually discuss some of these choices, like should this paper go here or there? Right? So they can have these small group discussions and make these finer-grained adjustments and then come up with a way to actually resolve the tighter constraints without kind of everyone, 200 people jumping in trying to grab the paper, so to speak. Okay? And the cute thing here is that these folks, the smaller group, also get actionable feedback, but their actionable feedback is different. Right? So the actionable feedback given to these folks are to kind of get coverage and to get enough session-making potential, right? You can think about that as collecting enough information so that the constraints, when you do solve the optimization problem, are not going to be as tight. And then you have this smaller group who have all that information, who can then make these finer-grained decisions and actually resolve these tight constraints. So coming back to this general challenge of engaging the community, for authors and attendees, we need new ways to provide relevant suggestions to them if the processes and tools are going to be any use to them, right? So we need to actually suggest, instead of showing them 400 papers to look at, we like to suggest relevant ones and, of course, to attendees as well. And here, you could just do a machine-based approach. So you could do something like document similarity with TF-IDF. For author sourcing, you could use a collaborative filtering algorithm for recommendations and build up a preference profile over time, right, as you collect more data. But it turns out we could actually do better than this. And the way we do that is through this idea that we call incentive chaining. Okay? And what this idea does is across the ecosystem, it's engaging increasing sets of ecosystem members by using the data that's collected from the earlier interactions to promote further contributions from others in the subsequent interactions, right? So we, for example, the expert categories that's generated from that committee sourcing process is coupled with TF-IDF to produce a short list of similar papers for authors. And the results show that you get a much more relevant list than if you just use the machine algorithm. And this list, of course, helps the authors focus their attention than having to scan the whole thing. And then the data that the authors provide, so we get something like 10,000 data points from authors, they become seeds into our collaborative filtering algorithm. And what that means is that we avoid the co-start problem. Okay, so the co-start problem is common in collaborative filtering where you have to like a bunch of stuff before the system knows how to give you good recommendations, right? But we just took all this data and then fed it as seeds, so we don't have a co-start problem. So very quickly, the system is usable and giving you really good feedback, and then you're like, oh, cool, let me see what other things it might recommend, and it allows us to scaffold data quicker. So on to step 2, helping organizers resolve these conflicts. So with all the data that we collected, we should just feed it all into a computer and optimize the schedule, right? Jim's shaking his head. No. Okay. So why not? Okay. So there's a couple of reasons for this. One of which is that if you think from the perspective of optimization, the problem is actually still highly underspecified, right? So we end up getting something like 10 to 20,000 data points. But if you think about it, for 400 papers, even if you're talking about pairwise relationships, that's 16,000. Okay, so we actually capture a very small set of the overall structure of the problem and the knowledge of what's going on. So computers can only optimize what it knows. So if you press the optimize button, it's going to give you some bad sessions. And the problem is, the chairs might not know those are bad sessions, right? Because we said the knowledge is distributed across the community. So you look at this thing, and then you try to fix it. And the process of fixing it is actually very complicated, especially if the system has no idea what it just did, other than fix the stuff that it knew how to fix. So furthermore, the chairs or anyone who's planning are going to have other goals that's not accounted for and not actually encoded as constraints, right? So you have all these tacit knowledge that the chairs hold, and you want them to be able to apply that and put their imprint on how they want the conference to be structured, even if some of those things are really hard to encode as hard constraints into a system like this. Okay, so let me show you how this works. So we have the second idea, which is a community-based mixed initiative interface. And this puts the organizers in the driver's seat and gives you a holistic view of all the constraints and preferences. So let me just play through a little bit of this, where you get this multi-dimensional view of the schedule for different things you might care about looking at. And as you go through, right, so you can look at personas, you can look at all these things. You see in red, these are the conflicts that still remain in the schedule, right? So some of these are hard conflicts. Some of these are community input, right? Things that community members said they wanted. And then you could propose a move to try to move a session, and the system recommends to you in green good swaps, things that if you made this swap would remove a lot of the conflicts that the system knows about, right? So you still leave the organizer in control to make these decisions because that's what the system knows, and now the organizer should apply what they know as well. And what's really exciting about doing this is that it allows the organizers to work on the schedule with confidence. Okay, so what we see here is kind of this process of resolving constraints, and the red line is the number of constraints that are left in the system. And what's really exciting about this is not just that the constraints are going down, it's that you have these areas where the constraints are not really changing that much, but the organizers are actually doing all this stuff to the schedule, essentially being able to improve the schedule in the ways the system doesn't understand, but without screwing anything up, right? Because the organizers can now make a change, and if that change is a bad change per community input and per hard constraints, the organizers know that. Okay, so you avoid those kinds of problems that come up. So let me share with you just some of the high-level outcomes of designing this ecosystem. We deployed Cobi at Kai and CSCW in 2012, 2013, and then 2014. So the data I'm showing you here is from Kai 2012 and 2013. Okay? So we have this inclusive process that at Kai 2012 engaged 1,500 community members in various phases of planning. It reduced the organizers' time from 100 hours, which is how dedicated the organizers were to try to fix all these problems, to 5 hours. Okay? And the organizers produced way better schedules because they were able to resolve all these hidden conflicts that they never knew about that the community wanted, because how would you know about it? Right? So I don't blame the organizers at all. The point is just we have these tools and we have these processes, we could do a lot better. So just to summarize this part of my talk, we designed a computational ecosystem for community-informed planning, and it gives us these collaborative planning processes and tools across crowds and groups. We have these ideas about incentive chaining to chain contributions across the ecosystem, right? And we also have these mixed initiative interfaces that empowers the organizers to make informed decisions by considering community input, systems recommendations, and also their own tacit knowledge. Okay. So any questions on this part of the talk? Yes?
How do you measure quality?
Good question. So the quality measures we have are just based on the information we have on hand, right? So the information we have on hand are hard constraints, of course, and then the community input. So when, say, to papers that a lot of people, so there's some kind of threshold we use, but a lot of people wanted to see, and they're actually being placed at opposing sessions, that would be a conflict, right? So part of this is that we're capturing more of the hidden conflicts that we couldn't before. Now, you could imagine there's like more hidden conflicts that we still don't know about, and that's definitely possible. But what we know is from last year's process, like these are the hidden conflicts that are actually in the system, but if you turn off these community-based constraints, you wouldn't have even seen them, right? And they're really hard to resolve. Yeah. So it's a within system evaluation, I guess. But yeah. Any other questions? Yeah.
Which other scenarios does this problem apply to, where there's a small group of experts and there are a large set of people with very limited knowledge, but it is still really useful? Have you tried it in some of the other domains?
It's a really interesting question. I haven't thought about that deeply, but I should.
Or to build on these questions, because I think the system is so compelling for all the different pieces that fit together really well, and it actually works amazingly well.
Thanks.
There are two things that the current version of the system doesn't do, but certainly could. One is room sizes.
Sorry, go on. I'll have something to say about that. Yep.
And the other is the value of having things that are related be close to each other, albeit non-overlapping.
Yes. I understand. And so on your second question first, the organizers actually try to do a lot of that by hand. So Wendy and Michelle in particular, they really wanted these thematic rooms, right? And they took the work to do that, and they mostly just used the personas to do that. But you could certainly imagine coding those kinds of things into a system like this. So we're providing at least some kind of visualization that helps you make those decisions.
Like papers that have the same authors should be proximal in time.
Right. Right. So, I mean, I think the nice thing about a system like this is that you can actually encode a much more flexible preference and constraints engine, right? And we started some work on that, and then people became faculty, right? And that's partly the answer to your first question, although the other answer is we didn't quite do exactly what you said about room sizes, but I did the following. So I knew we had the data from the attendee sourcing of how likely or what people said they wanted to see. And then I went to, I think, the 4 most popular sessions, and lo and behold, there was a line out the door, right? And it really made me, to me, that was like, we can actually do this, because we knew that 2 months ago, right? So I think, there's some practical things that, we've kind of stopped work on some parts of the system because we became faculty and so on and so forth. But, these are things that this way of thinking can allow you to do, and with these kinds of tools. So, thanks. Okay, so I'm going to move on and talk about this problem of scaling research training with the goal of, again, cultivating self-directed learners. Okay. So I'm going to get into this idea of self-directed learners a bit more here. And what we found is that if you really want students to be self-directed, so they could conduct independent research and do all these other things to learn, they're going to need what are called regulation skills. Okay. So what regulation skills are there's some goal you want to reach. What are all the cognitive, metacognitive, motivational, and emotional skills that you need to have to reach those goals, right? And in independent research, you need regulation skills, for example, to plan the work that you're doing and think about monitoring the progress of your work and replanning as needed, and also seeking help to overcome challenges. And that students lacking these skills are confined to doing either root tasks, or they can struggle to make progress because they'll do something and then they have to wait for their mentor to tell them what to do next. Or they'll be stuck on something for a really long time, not ask for help, and then wait till the next mentoring meeting, which could be a week or 2. So the thing with regulation skills, though, it's not to look at it and be like, oh, regulation skills are hard. I don't know if I have all of them. It's really hard to learn, right? And I think we actually do a pretty bad job of teaching them in general. And then instead, right, we have researchers, and this is the thing that really pains me because we have our brightest people, and then we have them bang their head against the wall. Sometimes for a really long time, and then one day they maybe figure it out, but maybe not, right? So there's got to be a better way, and that's what we're trying to look at as we look into this problem. Yeah?
So I want to question an assumption that
Please.
you might have to wait for a long time before seeking your mentor. A lot
Yeah.
of technologies now allow for people to interact quickly. For example, Slack.
Yep.
And I know that has really helped my work.
Yep.
So what do you
And what would happen if, Scott's your advisor, right? What would happen if Scott had 20 students and they all decided to Slack him all the time?
Okay.
Right. I'm thinking for Scott here. Like, we're thinking for the faculty, right? The time that is really hard to scale as the faculty. You could reach us more quickly, and that poses some benefits and a danger of sorts. Okay. So let me get into the model, and then we could talk more about this. So the model is called Agile Research Studios. It's a computational ecosystem, and it's a model for research training within a learning community. Okay. So all the students, regardless of seniority, conduct independent research and receive authentic research practice. And what I mean by authentic research practice is that they all go through the self-directed project cycle. So they set goals, they learn, they plan, they make progress, they reflect on what it is they've learned, and then they do this cycle again. Right? So all my students do this as they work with us in DTR. So the idea behind ARS, this model, is that it scales faculty time. So we've already talked a bit about why the apprenticeship model doesn't quite scale faculty time at scale. But you could also imagine doing a hierarchical model, right? So the faculty sits on top, you have grad students, and the graduate students mentor the undergrads. But one of the challenges is that being a good researcher and being a good teacher of other people becoming independent researchers are not the same thing, right? So this is a famous result from learning science from Shulman. And graduate students, as they're learning to master research, they're still just beginning to learn how to be mentors, right? So the students working under them are, again, often confined to root tasks that are just given to the undergrads. So what I want to do instead with this ARS approach is to build a dispersed control model, okay? And in this dispersed control model, the idea is that we're distributing the things that faculty typically have to do on their own to an entire community, being mindful about how we do that. Okay? And this is what's going to allow us to overcome what's known as the 1X challenge, right? So just one faculty responding to X or many students. And in particular, this ecosystem, ARS, is designed in such a way with processes, social structures, and tools that work together to help students develop these regulation skills. Okay? So ARS adapts Agile processes that we got from software development and design to research, to scaffold the self-directed research cycle. Mentoring is distributed across these social structures to support students planning research and also getting help within a supportive community. And further, we have these virtual studio tools that support learning through this Agile process and promotes effective interactions within the community. Okay, so I'm not going to be able to walk through every piece of this model, but let me just give you some vertical slices to get a feel for how this works. So let me first describe how we use ARS to support students learning to plan research work. So as I was saying, we adapt an Agile process. So my students do something called sprint planning. Okay, so some of you are probably already very familiar with sprint planning, maybe from software though, so I'll say a little bit of the difference. But every 2 weeks, my students set what are their goals for the next 2 weeks, and they write down stories and tasks. They also use points, okay, for people familiar with Agile. And they're planning out essentially a sprint, but not to deliver user value, but instead research value. Okay, and that's something that I'm not going to get into in a lot of detail in this talk, but I'm happy to chat offline about how we think about research value and helping students think about research value. So in this process, students are planning their own work, thinking about what they're going to do in the next 2 weeks. And what they do is they bring this plan in every week into a SIG meeting. Okay, so a SIG meeting is a meeting where we have maybe 2 to 3 student teams working in the same general research area. And we have a faculty mentor sitting in the SIG meeting at first, and the faculty mentor fades out over a period of years as a graduate student is being trained into a SIG lead. So my graduate students, by the time they graduated, would have trained about, I want to say about 8 projects on 15 students or so. So they really would have ran a mini research lab by the time they left the PhD program. Okay. So in these SIG meetings, what we have is that the students present their sprint plans and also progress and blockers on the second week, and we're giving them feedback on how to think about planning. Right? So we're not saying, what are your problems? Let us all fix it for you. Right? Instead, we're trying to teach them how to fish and think about, oh, okay, what are your options? Interesting. Well, which one is better? And then we walk through that and we scaffold and model that as well, of course. But the process is to teach students how to think through these problems, both by getting prompts from their mentors, but also from fellow students in their SIG. And then to support this, we have a studio tool called a sprint log where students record their sprint. It's basically like any sprint planning tool that you've seen before. It does have some additional prompts to guide what's called the regulation learning process. So it's asking them things like, what are your deliverables? What might be blockers you encounter, right? That you might not get in a professional tool, but we're putting those prompts in to help students think about these things. So this is an example of a SIG meeting. When Steve introduced me, I didn't know if I had Stella in my slides, but I do. That's Stella. She's just in SIG meeting to get petted and to offer emotional support of a sort, right? So Bomani, one of my students, is presenting what he's working on, and then you see all these other students working on different projects in the SIG, listening attentively and then giving feedback and helping him think through what are the different strategies he could use to replan or people he might need to reach out to that might be able to help him with what he's doing. So having talked about planning for a bit, I want to turn to help and collaboration. And the big idea here is that we distribute help. And when we say we distribute help, we're very serious about distributing help. Okay, so let me just give you one example how we do this. So we have a social structure called a studio meeting where we meet for 3 hours each week. It's almost like a class, and students actually get credit for this. But during that 3-hour meeting, we have all the SIGs come together. And then we use that time for students to help each other. We also do demo and critique. We also do some instruction so that we teach students how to think about research, how to formulate good arguments, and so on and so forth. So with the studio meeting, one of the things we do is we run this tool and the social process that's called pair research. And what pair research does is it helps pair students up who can best help each other. Okay, so let me just show you pair research, and this is me using it right before coming here. So I go into pair research and I'm typing in something that I need help on, finalizing the intro to my talk, right? And then other people are doing the same, and I'm rating how well I can help other people. Okay, so I'm putting it in like, okay, I could help him a lot, not so much, right? And then other people are doing this as well. And as I start putting in my preferences and everyone else is doing this, I could make pairs, confetti falls from the sky, right? And we get pairings, okay? And these pairings are optimal pairings in the sense that it's looking globally across your network and thinking about who are the students who could best help each other, taking advantage of all the expertise in your network, right? So let me give you an example. From a faculty's perspective, the system would pair me with the student who other people couldn't help, but I can, right? And generally it uses expertise in that way. So we're really fully leveraging kind of the distributed expertise that's in the system. And I wasn't going to talk about this, but just as an idea, maybe as I forget if it's a riddle or puzzle or a hint from the other session, but we actually purposely don't make perfect pairings. We just add a tiny bit of randomization so that if you pair recently, we don't pair you again. Or we pair you we're less likely to pair you again, right? And the thinking there is not so much to screw up all the optimality, it's to think about how skills can distribute across the network so you're not constantly pairing with the same person. So one thing I want to emphasize, pair research is very enticing and you should all use it, right? Like if it helps your research lab, but distributed help is not just one tool, right? So pair research is great. You'll get benefits with it on its own, but we have students who come into lab and just offer over-their-shoulder help when they happen to be there. We have Slack channels for all these different kinds of help that students might need. My students, the undergrads, started themselves a mentoring program for new students, an onboarding program this quarter. So this is just a mentoring heartbeat. So they have paired up one old student, one new student, right? And they're doing these kinds of things. The SIG meetings reveal a lot of the area student need help so they could make better help requests, right? And then we have these lists of experts that for anything you could possibly think of in design, tech, and research, who to turn to ask for help. We also have self-reflection, right? So this is a part I'm not going to talk too much about, but students do a 10-page self-reflection every quarter where they think deeply about their processes, and we do one-on-one meetings to think about how to support student growth through that, and help seeking is a part of that as well. So let me just show you some of the outcomes that we have in the first 3 years of this program. I've mentored 50 students in independent research, mostly undergrads, and they worked on 25 student-led research projects. Okay? They won 29 undergraduate research grants at the university. That's the most any faculty has probably ever won at the university, but certainly in the last 10 years. And then they published 11 papers and extended abstracts at major ACM conferences. And further, we have 4 student research competition winners, including Sarah Lim, who just won the Kai Student Research Competition this year. Yeah. And then the last stat is one that I'm actually really excited about, is that most of our students, by most I mean 96%, stay for at least 2 quarters. And most continue till they graduate. So Sarah is an example of someone who I think is on her 9th quarter. So she started really early, but we have students who just stay with us and continue to learn how to do research through this Agile process, learning to do it better, and better as they work on the project. So what's exciting is that beyond these outcomes, we see students we see early evidence that students are developing in their regulation skills. So these are some of the student-reported planning strategies that they're learning. So building at the fidelity appropriate for the current stage of the research, prioritizing important features and research questions, sequencing tasks, and in some cases, right, moving on despite uncertainty or imperfect knowledge. We've also seen that students are very willing to help each other, both within a SIG and across SIGs. So students help more than 1/3 of their studio each quarter. Okay, and that's not only from pair research, it's all the help that I was talking about before. So what I'm showing you on the right is from winter 2016, and each dot or each node is a student, and the colors are the SIGs. Okay, so what you see is there's a lot of help within the SIGs and across SIGs as well. And we see that not only is the help happening, students are actually developing help-seeking dispositions. So we have students say things like, I can ask for help, and that everyone asks for help, and it doesn't make them stupid to need help. It turns out that help-seeking is a really hard thing, and that undergrads and graduate students are often unwilling to do this. So even early evidence of this is encouraging, and we're trying to get better measures as we move forward in this project. So for faculty time, it takes me 10 to 12 hours per week to run this studio. Okay, so 5 of my hours, it's actually less now because some of my senior graduate students are leading their own SIGs, but 5 of those hours are for the SIG meetings. The studio meetings are 3 hours, like I said, and then I do about 2 hours of in-person office hours and 2 hours for Slack and virtual help. Okay, now of course on weeks where we're writing papers, it's a lot more than this, right? I don't have a way to scale that yet, but this is my typical week, and it's pretty good for this many students because when I first had I think when I went to 14 students was when I really started suffering. I was up till about 2 in the morning every day or every other day, just responding to students, try to keep them on track. And it was never going to scale if students didn't start developing the self-directed skills to be able to diagnose their own problems, help each other, and so on and so forth. So just to give you a high-level overview of all the SIGs and projects that we've been working on, right? So we have projects in 4 of these different special interest groups, and then those are all the different projects that my students have been working on within them. So we really have been able to, with scale, get more breadth and depth into the research areas that we're looking at. So I don't have a lot of time to show you all these projects, but I just want to highlight just one example of an undergraduate project that we worked on recently called McGonagall. Okay, so it's a design lab, and one of the challenges in design for mobile apps anyway is it's really hard to test them out in the world, right? That paper prototyping we know is a fantastic approach, yet testing a paper prototype out of the lab, it just doesn't work. It doesn't seem to like, what do? Do you change the paper? And you could do a paper in screen prototype, but now you lose a lot of the affordances of wizarding, okay? And what I'm showing you here on the left is dog ears, right? Like the Snapchat thing, and that's in the lab. On paper, okay, entirely on paper. And on the right is an AR interface that someone can take outside of the lab when the prototype was entirely on paper. Okay, so seems a little magical. So let me just describe briefly how this is working. We have a paper prototype that's in the lab, like I said, and then we transfigure it, right, McGonagall, right? We transfigure it where we turn the codes that are on the physical elements into their digital representations, right? So we would actually open up not only things like native maps and things like that, but also user-generated data. So someone could actually take a picture, and then the code would show the picture they just took, and you could actually interact with real data live in this design process. So as people use this app, right, out in the wild, they press things as they would, on a normal phone, and we get their gestures and stuff back into a command center that you could actually see as the wizard, so you could respond appropriately. So let me just show you a little bit of this for Pokemon Go. Okay, I'm going to show you Pokemon Go entirely on paper. Okay, so here we go. Oh no, let's see. Do I just press it? There we go. Okay, so right, here's the Pokemons, right? We have the map showing up right now. And as the person's walking, we could actually move this icon to show their position changing, right? It's part of the wizarding. And then as they walk out here, they're approaching, I think, that Pokemon up top. Someone knows what it is. I don't know the name of the Pokemon, the flying one. And then they click it. So now we're in like battle mode or something where you try to catch the Pokemon, right? And then the person puts on, the wizard puts on the Pokemon, the Pokeball. And then they put in this code of boom. Oh, wait, a little early. But boom, that's AR. Right? You're getting AR and you're getting the real interaction out in the world. And you could now start to understand how people might use a mobile app in actual situations of use with an entirely paper-based prototype. Okay? We call it mixed fidelity, but it's a mixed fidelity paper prototype. Okay? So this is really exciting, I think, and this was an undergrad project, which I thought was really great. Okay, so just to summarize, we have a computational ecosystem for Agile research studios where we're developing regulation skills for research planning and help seeking across all of these different ecosystem interactions. And further, what we're doing is that we're extending the scale and the capacity of a community to produce and learn, right? So instead of thinking, we have these critical resources that limits our capacity, we're really thinking about how do we leverage and grow the capacity of the network as a whole as we're learning in this way. Right? So there's some things that mentors can't possibly do, but with the ecosystem, you can. Okay? And that's the idea. So one question we're interested in exploring in future work is how do students develop these regulation skills? How might the development of these regulation skills within DTR actually help them beyond DTR, right? So beyond this ARS studio. So for me, training students to do research is so rewarding because of the regulation skills that it helps students learn, not only because of the research they're able to do. Because what the regulation skills do for tackling big challenges is it allows students to grow to be willing to take on big challenges that align with their own goals beyond school. Okay, so I really look forward to studying this in our continuing work and understanding better how this model is supporting regulation skills training more broadly. Okay, so before I move on to the latter parts of my talk, any questions on the Agile research part? Yeah, please.
Have you seen any example, this is all really cool, have you seen any example of where the wrong feedback or the wrong information has propagated and no one has been around to correct it?
Good question. Not too much, because we have a lot of, right, so the mentor is not entirely out of the picture, right? So we have the SIG meeting still. So when students come in and they try something, they're like, somebody told me this is how you design a study. And then we're like, really? What are your outcomes again? How do you measure them, right? So we have all these corrective things in place. Yeah, and then we work in an agile way. So often, failures get corrected pretty quickly. It's a good question, though. I might want to think a bit more about that one.
So
thanks.
on that note,
Yeah.
This is amazing. It's totally cool, and I want to incorporate a bunch of these practices into stuff we're doing here. I think it's great. One of the challenges with talking about the efficacy of different software engineering strategies, like Agile programming,
Yes.
is that the proximal measure is like lines of code.
Yes.
But that's not really what you want.
Exactly.
And in research, the proximal measure is things like Chi papers.
Yep.
But that's not what you really want.
Exactly.
And so
Right.
I'm curious if you have any thoughts on if you could kind of sketch what a better measure might look like.
Great. So we're actually working on a measure right now. So for example, let's talk about planning, right? So planning is something that requires regulation skills, but also requires you to have good conceptual knowledge of what's actually going on in the domain. So I won't get into this in too much detail, but we create these research canvases that actually teach students or scaffold students through making arguments. So essentially, we have this one-to-one mapping of a set of 80 questions or 40 questions on a practical canvas and another 40 questions on what we call the conceptual canvas. That essentially, if you could answer all those questions, you have a Chi paper, but the real conceptual understanding is really within these canvases. And what we're trying to get students to do is to learn how to think like that. And what happens, right? Students walk into a SIG meeting, they're not thinking like that. They just say, I have this problem. And it's like, you could spend 15, 20 minutes talking about that problem before you actually understand conceptually what's actually wrong with it. So that's what the learning modules are teaching. And we're creating tools right now, one of which called Polaris, where we're starting to use tools to help students diagnose issues in their argument and use that to guide what they do in their sprints.
And so, what that's points to is you kind of have a double objective function, or maybe not. There's clearly one objective function, which is train students.
Yes.
And it's pretty clear to see how this sings on that.
Mm-hmm, mm-hmm.
And obviously there's more you can do, but this is great.
Mm-hmm.
And the other one is the research itself.
Yep. Yeah, I think there's always going to be a trade-off between the two, right? To some degree. I think we've managed a trade-off in some. I don't know, right? People talk about this, right? I talk to people in industry like Anand, who's trying to get, crowd programmers, and he talks about like a 1.5x speed up by having a crowd worker. Mm-hmm. It's like a half a crowd worker. And we are actually, I don't want to share too many numbers right now, but we're starting to get the speed up. So it's actually, I don't know if this will hold, but let's just say it's between 2x and 5x.
Yeah.
In terms of how many, right? But again, it's not just about the papers, of course,
right.
but.
Because
right.
I'm not sure there's a trade-off there, right? If you were to plot good research, bad research,
yep.
Good training, bad training, you can
yep.
certainly find examples in all four quadrants.
The challenge actually is that there's another dimension. There's many other dimensions, but one is how long do you have the students for, right? And how willing are you to put in the effort? And often what I think about within ecosystems is, do I have the resources to meet certain needs that I might have, and how does that then inform how I think about training and producing research, right? So the larger question is, how do you think about ecosystem resources and needs at a higher level, and be able to inform your decisions and understand those trade-offs with that in your model, so to speak. But yeah, great question.
I like this work a lot, and we talked about this morning.
Mm-hmm.
Sort of, how do you scale it larger?
Right.
There's surely boundary conditions here, but
yep.
I was thinking during the talk, could you sort of recursively apply this? So here, I think that the motivation has been scaling your time.
Yep.
But what if you reapplied it to the second year a student
yep.
was in this kind of thing to sort of scale their time?
Yep.
And there might be a path there to really scale things much larger.
Yep.
Than you have.
I think so. I think I said this morning, even with the current model, I think we could actually go to 50 if we wanted to, because the teams are very small too. They're all 1 to 2 people teams. So the thing I always worry about, and I don't know if this is a reasonable worry, is that we can't, let's say we could do all that and it actually works really well. Do we lose something? And I'm afraid I don't understand what I might lose. And once I scale, I don't know how quickly I could crank it back because I currently don't kick students out of the class, right, the next quarter. They just keep enrolling and my community keeps getting bigger until they graduate, of course. But that's a great idea and we should think about that. Yeah, please.
I really enjoyed what I saw. I have a question about scaling not only size-wise, but
Yes.
scaling across other disciplines. And
Yep.
are you limited to a certain kind of knowledge base that you can distribute and
Great.
knowledge sharing that you can distribute using this system? Because this comes out of culture, the studio culture that you're talking about comes
Yep.
out of it's
Great
very common in
great
healthcare,
question.
very common in other
Yep.
fields that involve a physical presence,
Yep.
where you're learning through watching others.
Yeah.
It's common, right?
Yep.
But this has its own value because it's borrowed into another field. And
Yep.
the system is incredible. But do you see now if you were to bring this back into some of these other fields that
Yep.
require kind of
Yeah, so I'll try to answer your question, but I'll also borrow your question a little bit, if you don't mind, right? I mean, I think one of the things computer scientists often think about in scaling is just scaling, right? But when learning scientists or other people talk about scaling, it's like, how do you do it replicated across sites? How do you think about those kinds of problems and adjusting to variability and different cultures and practices at different places? And how do you do sprint planning in bio or whatever, right? Or even in theoretical computer science. So I think those are all good questions and things that we actually need to learn about. So that's one thing I'll say. I think a lot of the practices, would be useful even off the bat. The one thing I will say also is that the ecosystem model to me is a bit more honest. And what I mean by that is that it specifies, here's how we got it to work because we had these social structures in place, these norms in place, these processes in place, and with this, we could do this, right? There is a more, not more interesting, but also interesting research question of, well, how do you build those kinds of norms? How do you actually get this to grow into these other communities? That is something that we're actually starting to do. We're first just hosting people in our field. We're running a program called Agile Research University. I'm not going to talk about it too much today, but we're actually inviting faculty over a 2-day period, a 2 to 3 day period to learn how we do what we do. And then we spend that time designing their studio to meet their needs. So that's something new we're doing now. Yeah?
A question on a couple of the things that sound like other Agile concepts to me, right?
Yep.
Sort of gauging velocity.
Yep.
And then as far as the self-correcting thing, I'm wondering if you are incorporating other aspects from any particular framework like Scrum, where you're seeing that, so daily stand-ups and retrospectives.
Yeah, so I'm going to handle your question, but I'm just going to give a short answer for now, and I'm happy to chat more offline. I think one of the things we think about in adapting Agile is what are the constraints we face, right? My students aren't all in the lab every day. Doing a physical daily stand-up is actually really difficult when you have undergrads with very different schedules. Getting that 3-hour block is already pretty hard, and we actually often reschedule every quarter to make sure everyone can make that 3-hour block in the meeting, right? So kind of the challenges is how do you start adapting it to your situation, but then maybe there's opportunities for new practices as well, right? So, sorry, go ahead.
I guess, okay, maybe I got off a little on this to the side. What I was actually trying to ask about was the gauging the research value and the inherent property of Agile being it's allows for changes, right? You're trying to correct as you go.
Yep.
How is that happening?
Good. So I won't get into this too much, but right, students do a sprint. Their sprint may be to test a design argument or a hypothesis. They're going to get some feedback from their test, right? That might inform what they do, or they come in with an argument and they get critiqued on their argument, and that might change things as well. Yep. So some from the community, some from self-diagnosis. But I'm happy to talk about that more offline. Okay, so I'm going to move on and talk a little bit as a preview of what we're doing to advance the kind of system level thinking that's embedded in the examples that we've just looked at. Okay, so for my first preview, I want to talk a little bit about ecosystem level architectures. Okay, and what I think these architectures can do is provide these enabling technologies for coordinating activity across the ecosystem and support ecosystem members and proper ecosystem function by having this underlying architecture. Okay, so let me just give you one example of this in a domain that we call on-the-go crowdsourcing. Okay, and what on-the-go crowdsourcing is about is to motivate large numbers of people to contribute to solving local communal problems in their existing routines, right? So what you're seeing here is somebody who is picking up their own package, and they get a ping that says, hey, there's 3 other people in your dorm who have packages. Would you be willing to pick them up? And she did, right? And then now she's walking back back to the dorm and dropping these off. So a core challenge in enabling these kinds of on-the-go crowdsourcing systems is you have to balance what the system needs, right? All these tasks you want to get done, but also the contributors, right? You don't want to be overly disruptive of people's routines. So what you're seeing here as an example is there's tasks in many regions, right? So you can imagine this for lost and found, or if you're doing time banking, so all these different tasks around, and the tasks have different values, either because of priority or because of match based on your skills. Okay, and if you see someone walking this way, right, they're walking from this side to region 3, and region 3's value is pretty low, maybe what you want to do is wait, right? You maybe let them pass that region, and then if they happen to reach region 2, you hit, right? So you ask them for help in the places where their help is more valuable to the system. Okay, and by doing this, with this framework called hit or wait, which is making these decision theoretic kinds of trade-offs and thinking about when to engage somebody, we end up getting an interaction where we don't ever ping the person until we need their help, but somehow seamlessly, people just going about their ways meet the system needs, right? The global needs of the system. So I don't know how much of this you'll see from this video, but in this quick playing thing, so people are walking by, right, in these different regions, and the system is doing predictions of their routes and where they might end up, and thinking about, in this decision theoretic way, how can I get the people's help in the areas that's most needed, but accounting for the fact that people might not actually go to the region with the highest value, right? If you actually wait for people to go to the region with the highest value, it's a terrible strategy because you actually miss out on a lot of opportunities, right? But you want to think about these trade-offs, and you don't want the user to have to think about them. You want the system as an architecture to be able to support that, okay? And what I'm interested in for this, other than just for ecosystems, is that in these community-based tasking scenarios, you could not only imagine this as being a way to be efficient, but it's a different way to think about building communities, right? Where by having these convenient contributions that are along your routes, but that are actually helpful to someone else, you can actually think about connecting community members to this different kinds of interactions that may be quite valuable for building social capital and other things in the community. Okay. So in another direction, we've been thinking more deeply and more thoughtfully about mixed initiative interaction, but thinking about what mixed initiative means when you have a whole ecosystem with all these machines and possibly many humans, and thinking about the combination of integration and also of decomposition of roles to craft these new human-machine systems. Okay, so let me just give you one example of this called readily available learning experiences. And what this is that we're trying to make every real-world artifact into a real learning resource, and in this case, we're doing it for all websites. Okay, so all professional examples. So in this example, what you're seeing is the Tumblr homepage, and you might play with it and be like, whoa, that's really cool. See that scrolling effect? Tumblr has one of the best scrolling effects on the web. I want to know how to do that. How do we build a system that for any web page, any artifact out there, we could help someone build a conceptual model of what's going on here? Right? And before, we might have just showed people, oh, these are probably the lines of code where you do it. But that doesn't actually help people build a conceptual model of the design patterns and the stuff that goes into it. Okay? And we can't do this easily with an automated tool either, like intelligent tutoring systems, because again, we don't actually have a model of the underlying problem and example. So let me show you the first part of this. It's through a system we recently developed called Isopleth from my student Josh Hipschman. So what we're seeing here is the National Geographic website where they have this really cool New York skyline thing going on. And as we look at this example, we can go into it and start to inspect this condensed call graph, looking at all the different things that are happening through these aspect filters, right? So these filters at top allows us to see what are all the things that went through the AJAX process. What are all the things that are not related to keyboards? And as we do this, we could also define our own custom aspects, right? So things on inputs and outputs that show just a slice of the code. And what we're doing is helping people to start engaging on this iterative sense-making process where they could go in and look at a piece of it and say, I wonder what's going on here. Okay, and you see these purple lines, which gives you the async bindings, right, for JavaScript. So you could actually see invocation from the function calls in these links as well. You could go in and start labeling things as you understand pieces, right? And you do this thing where you're almost putting together this puzzle. You're trying to understand these pieces and understanding, oh, that's what this does. Oh, if this does this, then I could actually go over there and understand that as well. So I'm really excited that these approaches, right, using a mix of humans and machines and the learner, can start to build conceptual models on arbitrary professional examples on the web. But actually, that's just the start. So the thing that I'm really excited about is this leap that we're trying to take right now. So instead of focusing on mixed initiative tools, we're designing mixed initiative scaffolds in which the learner created artifacts, so what the learner did in trying to do the sense-making process, is used in conjunction with automated methods to create the desired scaffolds for another part of the learning process, for example, for implementing concepts or applying concepts. Okay, so the idea is that you could take learner-generated conceptual models and use the labels they generate and the machine labels to decompose into scaffolded exercises. That's something the machine couldn't do, but because you have the learner labels, right, and you scaffolded that part of the learning, the machine can now provide the next exercise. And as humans do stuff here, the machine can then do this, and so on and so forth. So you're actually building a closed-loop ecosystem where the learner and the machine, or many machines, right, many tools, are collaboratively doing something to support learning that no software tool by itself could have done a priori, right? So I think this idea could be really powerful, so I'm really excited to explore it in more detail. So just as a summary, we are thinking about this kind of system-level thinking with these ecosystems, and I just really think that this way of thinking about problems is going to be really useful for devising scalable solutions for a diverse range of human problems. So to end my talk, I just want to end with a few thoughts on the role of technology for advancing human values at scale. So it feels to me that we're at a critical stage in humankind right now, so it feels like the right time to talk about it, even if it feels a little premature as well. Okay, so there's some caveats I want to say, right? So a lot has been said about human values. I did not discover them, right? If you want to learn about human values in HCI, read Bhatia's stuff, for example, Bhatia Freeman's stuff. You could also read about philosophy. There's a lot of stuff, right, from a very long period of time about human values, and I'm not trying to rehash that here. Okay? And people don't share the same values, right? So I'm not trying to say, oh, just follow my values, right? We might have different values. What I do want to say is something about scaling with technology for some value that you care to scale. Okay? So I think there's a real opportunity for computing, right, to be helping us with scaling, but it's naive to think that technology will undoubtedly scale solutions that just make everything better, right? So this is a quote from Nicholas Carr in his book, The Shallows, where he says, "The net's interactivity gives us powerful new tools for finding information, expressing ourselves, conversing with others, but it also turns us into lab rats, constantly pressing levers to get tiny pellets of intellectual and social nourishment." Okay, so a little concerning. Now, you might not take Nicholas Carr entirely seriously. You might think he's being a little dramatic, but these kind of compromises that we might make when we have a powerful new technology is something that could be quite chilling and something that could happen. So this is a short story that I recommend everyone read. It's called The Machine Stops. It's from 1909. Okay? And it's about this world, again, written in 1909, that looks a lot like the technology golden age of today. So they got, I think they got augmented reality, they got the internet, they got social media. So they got all the big three, let's say, that we're starting to get, right? But the story is not really about that. It's a story about us giving up on certain things about ourselves when we start to accept things as good enough and just service the machine, right? So the machine may progress, the machine may progress, the machine may progress for eternity. And there's a passage early on in the story from a boy to his mother, it's just these two characters in the story, that to me is at once heartwarming and really heartbreaking. Okay? And the boy says, "The machine is much, but it's not everything. I see something like you in this plate, but I do not see you. I hear something like you through this telephone, but I do not hear you. That is why I want you to come pay me a visit so we can meet face to face and talk about the hopes that are in my mind." Right? And I think the idea here is just that as we're scaling, it's not easy, but it's easy for us to scale what we can. And then we miss the point, right? That there might be things that we can't scale that we really hold dear, that we care about. And this is another quote from Paul Davidoff, who writes about planning in 1965 for city planning. And he talks about this idea that we cope with the problems of the alienated man with a recommendation for reducing the time of the journey to work. Okay? So this is another example where we're trying to scale, and if we only know how to scale this, then yeah, we could scale that, but what's the problem that we're trying to solve?
But that actually works.
Sorry?
But that actually works.
Say more?
Well, I mean, one of the strongest predictors of alienation is time of journey to work.
Yeah, okay, so there might be particular things that come up in how these values can actually be led by these things. But I think the point he was making is that as designers and as people doing these kinds of things, we need to actually have compelling visions of what it is we want and think about how the technical work we do might be helpful with that, right? And I'm happy to talk about what you just said offline, just in the interest of time perhaps, but I'm not convinced entirely on what you said, right? I'm not sure if I believe that because we could now travel 20 minutes faster or have an automated car,
I
right?
said they're correlated.
Oh, yes. Sorry, I'm not disputing that. Yes. Great. Okay, so just to end, if you really want to align your work with your values, right? And this is really what I thought this talk was about. I think we need to be mindful of what our values are. We need to look beyond the limits of technology, of what technology already offers us. And then I was going to write scale, but I wrote learn to scale. I think we have this assumption that scaling is adding more cores and more servers, right? It's computer scientists, it's not everyone, but I think scaling is actually something that to me was deeply humbling, to really think about it as a learning practice where all the intricacies actually come out when we think about scaling, both in the ways I've been talking about and the way that you were mentioning in your question. And I hope what I've done today is to show you how we could start to build new knowledge and new ways of thinking to do that, right? And that computational ecosystems is a step in that direction by applying what I've been calling ecological thinking and computational thinking. And if we're going to be a part of these systems that we're designing, then we should embrace both design and technology's power, but also remember and embrace our deepest needs as humans. Okay, so with that, I'd like to thank everyone on the Cobi team for the work on community-informed planning. I want to acknowledge all my students in DTR who's worked so hard, because it's not only the research work, they actually are pushed to be thinking about their own regulation skills, right? There's a lot of emotional challenges in learning that way, but they've done just amazing. So I bolded the PhD students on the top, and then my faculty collaborators are in red on the bottom. And this work that I showed you today really wouldn't have been